Hello everyone, I am Pushpita Chandra. I am a PhD student at IIT Delhi and aim to join PhD program in the field of physics. So I am the TA for the course Applied Optics. So let's start today's class. So before diving into Brewster's law and Melon's law and so on and so forth, let's discuss something about what is polarization. So in electromagnetic theory, light is considered as a transverse electromagnetic wave, considering of vibrating electric and magnetic vectors at right angles to each other, and also at right angles to the direction of propagation of the light. The electric vector is called light vector because it is responsible for the sensation of vision, and that's why it doesn't like associated with magnetic field so much. In an ordinary beam of light with millions of waves, the light vectors of component waves will remain in all possible direction on a plane drawn at right angle to the direction of propagation. This happens due to the random orientation of excited atoms or molecules in the source. Such an ordinary beam of light with the electric vector arranged symmetrically about the direction of propagation is called an unpolarized light. So basically, if this is a direction of propagation, then electric vectors can be in any direction. Like direction also that one is into the paper and another is out of the paper. And this is called unpolarized light. Okay. We can assume that all these vibration to be resolved into two rectangular components of equal amplitude but having a relative phase difference which varies rapidly and randomly. Now, if by some means one of this rectangular vibration is cut off, we get vibration of all the component waves confined in one defined direction. And that light is called plane polarized light. So in plane polarized light, in only one, the vibration of the electric vector is only one direction, either this or this. So these are called plane polarized light. Or E-state light. So the electric vector of the plane polarized light is confined on a particular plane known as the plane of vibration. The plane contains the electric vector and the propagation vector. The plane perpendicular to the plane of vibration is known as plane of polarization. Now, you will later know that there are other different kind of polarization apart from plain polarized light. There is circularly polarized light, elliptically polarized light. Right. So, when does this circularly polarized light happens? That if the superposition by the superposition of two plane polarized waves under suitable condition, the resultant light vector may be made to rotate in a plane perpendicular to the direction of propagation, and the magnitude of the each light vector is almost same, then uh, the tip of the light vector appears to trace out at a circle at a fixed pace. And this kind of polarization is called circularly polarized. And it can be clockwise and anti-clockwise both way. Polarized light, circularly polarized light, and elliptically polarized light that can be clockwise and anti-clockwise. So if it rotates as a clockwise, then it calls light circularly polarized light. Light circularly polarized light, or right elliptically polarized light. And if it rotates anti-clockwise, then it's called left circularly polarized light or left elliptically polarized light. It's like, and for elliptically polarized light, you might have been guessed that the two plane polarized light, which after that the of which the combination is that electrically polarized light, their magnitude is not equal, and that causes the and the angle. You later know that the angle is also important, and that creates elliptically polarized light. That's it. So basically, if this is the propagation direction and this is the light vectors, then this is actually plane of vibration. And this is actually plane of polarization. So now question arises how we can create like polarized light. So for that matter, there comes the concept booster angle. So basically, when like it depends because that when we know from the electromagnetic theory that there is a reflection coefficient and transmission coefficient and the square of actually not square, it's the reflection coefficient and the multiplication of the conjugate of the reflection coefficient is called reflectivity. So the reflection coefficient is denoted by small r. We can get this thing from Fresnel's equation. Similarly, there is a transmission coefficient in small t, and we got to know reflectivity. That is basically r star r. And then come transmittivity. That is t star t. So from Fresnel's equation, get to know so from Fresnel's equation we get to know and also the reflectivity for the parallel um, polarized light or parallel linearly polarized light and the reflectivity in the perpendicular direction is not same. So the for the linearly polarized light or whose electric vector is parallel. When we say parallel and perpendicular, parallel means parallel to the direction of the propagation and perpendicular means that perpendicular to the direction of propagation. So that's denote tan square theta I minus theta r, and in denominator it is tan square theta I plus theta r. This formula comes from electromagnetic wave calculation. The reflectivity for the light whose electric vector is perpendicular to the plane of incidence is given by sin square theta I minus theta. Sorry, parallel and perpendicular means that the electric field is parallel to the plane of incidence. and electric field is perpendicular to the plane of incidence. So arc perpendicular can never be zero, but arc parallel is indeed zero when the denominator is infinite. When this became infinite, when theta I plus theta r becomes 90 degree, tan square tan theta I plus tan theta r, because becomes infinity. And that's when arc parallel becomes zero. For this reason, if an unpolarized beam incident an angle for which theta I plus theta r is 90 degree, the reflectivity of the parallel component is zero. That means all the parallel light will be transmitted. So only the perpendicular light component will be reflected, and we will get electric vector in only one direction, and that's when we get the polarized light. So it's basically like this. The perpendicular component, part of it's not like that all the perpendicular component will be in the reflected light. In the transmitted light there will also be a perpendicular component. So we denote this is unpolarized light. So in reflectivity, as the reflectivity for the parallel light becomes zero, only the perpendicular component of the electric vector will be present. But in the transmitted ray, both will be present. This assumption is very important because that's the key. That in the transmitted ray is not polarized, only the reflected ray became the polarized light, only having electric field component as the perpendicular of the plane of incidence. And this angle for which this happened is called Brewster angle. So if theta I is theta P, then theta R is 90 degree minus theta P. So we know N is equal to sine I, here it is 1, basically. And this angle is also 90 degree. Okay. So they are all 180 degree. So if this angle is 90 degree, then this angle and this angle becomes 90 degree. So 90 degree is equal to 90 degree minus theta p plus something theta refractive index. So that means this is also almost equal to theta p. Okay, sorry. It is also theta p, and this is 90 degree minus theta p. So sine I is sine theta p here, and sine R is 90 degree minus theta p. So that becomes sine theta p by cos theta p, that is tan theta p. Okay. So n, you can say that it is n2 by n1 also. Here we were assuming that this is air, but if that is n1, this is n2, then this is more correct, appropriate expression. So in that case, theta p became tan inverse n2 by n1. And that's how we calculate Brewster's angle. We came to another important law which has been discussed previously in the class also, that is Malus law. So if you consider a polarizer which has a path axis parallel to the x-axis, then if an unpolarized beam propagate in the z direction and incident on the polarizer, only s-axis part will come. Came out. And then if it for so on another like polarizer which can be P2, the whose path axis is at angle with x-axis, then the intensity will change, and it will be the function of the cos squared theta, or the angle theta, that is the angle between the path axis of the first polarizer and the second polarizer. Basically, if it is unpolarized light and there is a polarizer, it has a axis along x, and after that we will get only this axis. And then we got another polarizer. Now we need to calculate the theta like this, where the angle between the two polarizers. Then it will become like this, and this intensity is I0 cos squared theta, and this is actually I naught here. Now we have seen Brewster's theorem by which we can generate plane polarized light. We can also produce polarized light by double reflection. So what is double reflection? So basically, for some crystal which is not uniform crystal. They are like calcite. So calcite is calcium carbonate. Say so they have two axes, and on those two axes, the beam travels in different way. So in one axis, the ray obeys the Snell's law of refraction, but on another axis, it doesn't obey Snell's law. So the ray that in that axis where on the ray obeys Snell's law of refraction is called ordinary ray, and the second beam, which is generally doesn't obey Snell's law, is known as extraordinary. So basically, that happens like this: that light enters and it like divided into two. So in one axis it goes like this, and another axis like this. So in one axis, like, and this is basically ordinary day, and another axis is actually extraordinary day. It doesn't obey Snell's law. The case. So it obeys, and later we will see which law they like. It doesn't follow Snell's law, then which law that refractive index obeys. Substance is called an isotropic substance. There's calcite and quartz and all those things. So they obey this relation 1 by v square is equal to sine square theta, where c by n e square plus cos square theta, where c by n o square. Okay, that's the thing. So in some books you will also get the like proof of this relationship, and also you can get the proof of that fact that this angle is 90 degrees. They are very easy proofs. This angle are 90 degrees. So seeing this equation, you get to know that is almost ellipse. This equation denotes ellipse basically. This function, it belongs to Snell's law, so that E is equal to C by N naught and NO basically. So NO is refractive index along refractive index of ordinary ray, and A is refractive index of extraordinary ray, or along that line. So always remember that ordinary and extraordinary, they are basically axes. So the optic axis, where the uh, the speed, uh, they have the same speed, that external ray and ordinary ray both have the same speed, is called optics axis. Okay, so along the optic axis n not equal to n, but in other direction they are not equal because their velocity is not equal and their velocity follows an angle. So it only like this phenomenon can only be seen in certain substance. This certain substance has two different crystallographic axes, and because of this, their internal what should I say? Because of their internal structure, these things happens. For like calcite was this phenomenon, this substance exhibit this kind of phenomenon. So when O ray and E ray both are traveling along optics axis, they travel with speed c by n. But when E ray travels perpendicular to optics axis, the velocity is c by n. So that's what I was trying to say, that even it is extraordinary ray, but when it is traveling along the optics axis, it has a velocity same as the ordinary ray. But when it travels perpendicular to the optics axis, its velocity changes from c by n naught to c by n e. Not v like velocity of extraordinary ray and ordinary ray, we can see that this is the velocity, this is the profile, and this is the profile for ordinary ray. And depending upon which is greater, which velocity is like velocity depends on the refractive index, and depending upon at which axis refractive index is greater, there is two type of like anisotropic crystal. One is negative crystal and another is positive crystal. In negative crystal, NA is less than N, that means VE is less than VO, and we denote like this. So this is actually optics axis. In optics axis, both move with the same velocity. That's why they touch here. And the positive crystal, Ne is greater than NO. That means VE is less than VO. In that case, V naught is bigger. That means in the optic axis they will be the same, but at the perpendicular direction V naught will be bigger. That means ellipsoid will be inside the sphere. So you need to remember the thing that for negative crystal, extraordinary ray has velocity greater than ordinary ray. And we know that in optics axis there is the velocity is the same. So that means this condition we are talking about, that extraordinary wave have greater velocity than ordinary wave, is in the direction of the perpendicular direction of the optics axis. That means sphere is inside of the ellipsoid, and for positive crystal it's opposite or vice versa, that we know that our optics axis both will travel at the same velocity. So we are talking about the perpendicular direction of the optics axis. That means here the velocity of the extraordinary ray should be less than ordinary ray. So ordinary ray is always its velocity is sphere. So that means sphere needs to be bigger than ellipsoid. So that means ellipsoid will be inside the sphere, and along the optic axis they will always touch each other. So now, how the refraction will happen for a plane wave of normal incidence, that we can discuss, or it has been discussed in the class. So follow the class PPT for that, because they have explained it well. And like it will take more time here to draw those things and of explain. So I'm not doing that here. So you need to consider reflection of plane wave. One is normal incidence. Oblique incidence. Umbrella of this parallel incidence and oblique incidence and so on and so forth. There is always like how the optics axis is being placed. So the optics axis is in the plane of the paper or the optic axis is like perpendicular direction of the paper or something, normal to the page and all those things. So if this is the optic axis, so then these are like this, like these things are like this, and the optic axis are like this. We'll see like this and this. Like this. And that has been discussed in the class, and you should remember those discussions. And what will happen if the optic axis is like the plane wave incident obliquely on the negative axis crystal, and both the cases for negative axial crystal and also for positive axial crystal. So it can be many things, but how the things unfold, that's that, like you need to practice that and think about that. It's nothing about to gulping and writing in the exam, but you need to just like need to know how this thing happened. That if this is optic axis and the negative crystal, this is how the wavefront slides. So this is for positive crystal, and this optic axis become oblique. Then what will happen? So this will happen this, and this is the plane of incidence. So we need to remove that part. So we'll only get like this. So when plane wave, normal or oblique, and for negative and uniaxial, and also how the optic axis is. That optic axis is normal to the page or parallel to the page. So you need to consider is negative, positive, optic axis normal or parallel to the page, all the 6 cases. Now we move to how we are gonna produce polarized light. How do we make that? So before that, I want to share interesting things like I have discussed Polaroid here, that but we can say a polarizer here to discuss the Mann's law. So intensity became less. It can also become zero at some theta angle. And if it is a unpolarized light, after the one polarizer, the intensity is basically half. That's the trick. So when unpolarizer goes to first polarizer, it's become basically half. So have you guys noticed that we cannot like keep our eyes open for a long time when we see sun in the daytime? But if we put sun glass, then we can see. And also when in a very bright sunny days countries like Australia, New Zealand, people always fix some things, and it soothes your eye because actual sunglasses, like they are actually have a good polarite in them, so that the intensity got reduced so much. Mm. So to produce that, we can use many like procedure. First is like the wire grid polarizer. And Polaroid. And so one example of Polaroid I have mentioned, like just mentioned that it's happen when the sunglass it has been used in sunglass. So for mm, okay, so where this happen, it actually a large number of thin copper wire plates very parallel like this, and the distance is not only this, they are very closely spaced. So the, when unpolarized light fall on them, sorry, then only one like direction passes through. So the component of the electric vector along the length of the wire is absorbed because this wire doesn't let pass this component. Only this component get passed. Because the electric field does work on the electrons inside the thin wires, and the energy associated with the electric field is lost in the Joule heating of the wires. On the other hand, since the wires are assumed to be very thin, the component of the electric vector along the perpendicular axis passes through without much attenuation. So for the effective wire grid polarizer, this spacing, if this spacing is spacing is d, d must be less than equal to lambda. So it is very hard to make wide grid polarizer for like visible way. So in Polaroid, what happened? These long chains are made by polymer molecules. So when a polymer light beam is incident on such a Polaroid, the molecules absorb the component of electric field which is parallel to the direction of the element alignment, because the high conductivity provided by the iodine ions are component perpendicular to it, passes it through. So basically what happened that the high conductivity of iodine ions, electric field that which is the parallel to the direction of the alignment got absorbed, and the component perpendicular to it actually passes through. And another way we have learned about the Brewster angle, that means by reflection. Reflection basically. So we know we need to make the wave incident on a Brewster angle theta p, which is tan inverse n2 by n1. In the reflection we get plane polarized light. So basically there is like this is only this, but it will also contain some perpendicular light. So let it fall in another interface class. Then it will go again perpendicular direction. Again, it will have some perpendicular, some parallel, and so on and so forth. At the end, you will get almost polarized light in reflection and in transmission. That is polarization by reflection. So for common knowledge, if you put these values here, you will get that for air and glass, N1 is equal to 1, N2 is equal to 1.5, so theta P became 57 degree. But for air-water interface, N1 is equal to 1, N2 is equal to 1.33, theta P becomes 53 degree. The third way to produce polarized light is polar double refraction. And what is double refraction? We have seen that we need to use the light needs to enter into an anisotropic crystal. Then it splits up into two beams, each being characterized by a certain state of polarization. We could eliminate one of the beams, or by absorbing the beams in the, like we can cut this unicrystal axis like this, the optics axis in such a angle that one beam can be absorbed inside the crystal. We can do that by like a crystal like tourmaline and all those things. Mm. And another method of doing that is that we make one beam totally crystal, one beam get absorbed, or it suffers. Total internal reflection. Okay. And another simple way is by scattering. So basically, all these ways are here. It is because of absorption. What is the key thing that you need to remember? It is because of absorption. Here, it is by reflection. That is the main purpose. Here, it is refraction. And here, it is by scattering. So if we put in also double reflection, also absorption and reflection has a part. That's the thing, because it's not only refraction, it is absorption also, and a reflection or internal reflection, precisely to be precise, has a part to play. Oh, sorry, the meeting got dropped. Scattering, that an unpolarized beam is allowed to, in the scattering gas, the unpolarized beam is allowed to fall on the gas. Basically, then the beam scattered at 90 degrees to the incident beam is linearly polarized. Then the beams, this follows from the fact that the waves is propagating in the y direction and produced by x component of the dipole oscillation. The y component of the dipole oscillation will produce no field in the one direction. If the incident beam is linearly polarized with the electric vector along the x direction, then there will be no scattered light along the x-axis. So that's how it works. And how we can do that? We can use, like, not by scattering, the way how we like have two polarized light, and what is the call of device, name of the device, that is Woolstone prism. Stone prism. Prism, and another is Rochon prism. And they has been discussed in the class very thoroughly. So in Woolstone prism, what happened, that the two prisms are there in Woolstone prism. And in the Ron John Olmsted prism is used to produce two linearly polarized beams. So in this prism, two similar prism with one optic axis of the first prism parallel to the surface and optic axis of the second prism parallel to the edge of the prism. That's how it like built, or one they are parallel to the surface. This is surface, and they are parallel to the edge. That means like this. And for Ronjon prism, it's like opposite. So the optic axis of the first prism is normal to the face of the prism. So here it is basically like this. Like this. And the second prism has the optic axis parallel to the edge. This part and this part is similar. This part and this part is different of two axes. Okay. So by doing this, what happened that here, when this is unpolarized light, when they exit, you can have two lights. And here it's like one light is there and one light in this direction. So now we can dive into the question answer part. So first we will discuss some question from the previous year quiz. First question is, Brewster law is related to which phenomena? The options are refraction, C is dispersion, D is interference. You all know the Bristol's law is the Bristol law does help in the uh, producing polarization. So this is the answer. And question number 2 is at Brewster's angle, the angle between reflected and refracted rays are A 90 degree, would be 45 degree, C 60 degree, D 30 degree. And I told you that there is a like proof for that. How does we prove that? So let's go with the proof. So it's like this. Angle. So it has both the perpendicular and the parallel component. That will be. And we have only this and they are both. So let me that is P, that is N, this is A, this is A, this is A, that is O, that is V, that is R, even dash, it is T. This angle is theta P, so this is also theta P. So from Brewster's law, if this is air, this is something else, then M1 is equal to 1. So from Brewster's law, you can know that tan theta P is equal to N only, not into by N1 N. That is basically sine theta P by cos theta P. From Snell's law, we know that n sine theta p equal to 1 sine theta p equal to n sine r. So n is equal to tan theta p and n is equal to sine theta p by sine r. So this is what? Sine theta p by cos theta p. If you compare this to result, that means sine r is equal to cos theta p. So cos theta p can be written as sine or any of this can be written as cos theta p. Sine r can be written as cos 90 degree minus r. So theta p plus r is 90 degree and that is r. So theta p plus r angle ROT is 180 degree. And theta p plus r is 90 degree. So ROT is 180 degree minus 90 degree is equal to 90 degree. So that is our answer. It is 90 degree. Then the next question is, the reflected light at Brewster's angle is A, circularly polarized, B, unpolarized, C, linearly polarized, and D, elliptically polarized. So basically, as I mentioned in the at the beginning of the class, so circularly polarized light actually the tip of the electric vector will rotate like this, either clockwise or anti-clockwise. That is right-handed, this is left-handed. For electrically polarized light also, it can be like this. So it can move like this, or it can move. It can move in this direction. So I previously mentioned that only one, like, if unpolarized light reflected at crystal angle, in the reflection we will get perpendicular polarized light, that is actually a linear polarized light. So this is the answer. Question 4. Brewster's angle depends on the wavelength of the light, b, the frequency of the light, c, the refractive index, and d, the polarization of the light. So we have seen that theta p is tan inverse into minus n1, and they are basically linear dependent of refractive index. Question number 5 is, from a certain medium, Brewster's angle is 56 degree. The refractive index of the medium is 1.48, B 1.33, C 1.4, D 2. So in that case, we are assuming that N1 is basically 1. This is air. So N1 will be equal to 1. So tan theta B is N2 basically. So tan 56 degree is N2. One 0.4825. So answer would be 1.48. Question 6. If unpolarized light passes through a polarizer, the transmitted intensity is a sum of initial intensity, B 50% of initial intensity, C 200% of initial intensity, D 0. So if an unpolarized light, the average transmitted intensity through an ion polarizer is basically half. I have mentioned that before also to solve a like question. Yeah, according to the Malus law. So the question is like that a 16 watt per meter square intensity light falls on to a set of polarizer. First polarizer is 50 degree with the optics axis. And the next polarizer is 20 degree with the optics axis. So the approach was like that unpolarized light, if it was unpolarized light, when it passes the first polarizer, intensity got half automatically. Then it follows I naught cos square theta. Theta here is the theta between the angle of these two polarizers, 50 and 20, that becomes 30. So cos square 30. But if the first it is not unpolarized light, it is polarized light, then after the first polarizer itself, it follows the Malus law. So this line is very important. So this is answer B. Question 7. Is if the transmitted intensity (25% of the initial intensity), the angle between the polarization of light and polarizer's axis is A 30 degree, B 45 degree, C 60 degree, D 90 degree. So basically, it is I by I naught is equal to cos square theta. That is 25%, that is 1 by 4 equal to cos square theta. So cos theta is equal to half. So now we know theta is equal to 60 degree. That is the answer. Question 8. The correct statement for the auditory wave of the ordinary ray in a double refraction material is it is absorbed by the material. B. It travels with the same velocity in all directions. C. It gets scattered. D. None of this. So the answer is it travels with the same velocity in all direction. Similarly, question 9 is the E ray in a bi-ray fringe and material A always travel at the same speed as the ordinary wave, which is wrong. Not always. Okay, just wrong. B obeys Snell's law, which is also wrong. C doesn't obey Snell's law, which is right. And D none of this. The options are not that good, basically. Question 10. Double refraction can be used used to create polarized light. B. Split light into different wavelengths. C. Increase the speed of light. D. Minus. So we know it used to create the polarized light. Now we will discuss one question about Maggie's law. That the electric field of 1,000 watt per meter square linearly polarized light beam oscillates at +10 degree from the vertical in the first and third quadrants. The beam passes through two consecutive ideal linear perpendicularly ideal linear polarizers. The transmission axis of the first is at 80 degree. minus 80 degree from the vertical. In the second and fourth quadrants. Of the second is at plus 55 degree from vertical in the first and third quadrant. How much light emerges from second polarizer? B is interchange to polarizer without altering their orientation. And determine the amount of light that emerges. First, the incident light is polarized. And here, one thing is that they are given like this, that first and third quadrant. That is mean this is first, second, third, fourth. So plus 10 degree. So basically this is plus 10 degree. Okay. Then this is say second quadrant minus 80. So second and fourth quadrant, that is actually minus 80. This is 80 degree. And this is minus 80. This is again 55 degree. This is 55. So minus 80 matlab plus 10 in second quadrant. So second quadrant angle starts from this line. That's what this happened. So for the first case scenario, the angle between incident light and polarizer. So in that case scenario, first polarizer is called polarizer The second polarizer is not called polarizer, they call analyzer. Always. The consecutive ones are called analyzer. Angle between the at polarizer is 90 degree. Cos 90 is 0, so no light. A second case scenario where first it's like 10 degree, then it will be 55. So if it is I naught, then it I naught cos square 50 minus 10 degree, which is I1. Then this is like this. So I2 would be I1 cos this 55 and 10, that is 65 degree. So 90 minus 55, which is no, it was 65 degree, that is 45 degree actually. So here it is 45 and it's 10. Not 45, actually 35 plus 10. 35 plus 10. That's 45 degree. So basically I2 is I naught cos square 45 degree to cos square 45 degree. Cos 45 is equal to 1 by root 2. So basically I naught into half plus into half. I naught is 1000. 1 by 4, that is 250 watt per meter square. So that is for today. And if you, it's very preliminary easy stuff in this week, module 10. So if you have understood that our last question and some question I have discussed, I will be able to solve the quiz questions. Thank you.